Okay, this little lesson here, we're going to go over the mean value theorem, one of the theorems we need for the class. So you can see there that the hypothesis, so the necessary conditions for this, is that the function's continuous on a closed interval, okay, which would mean that the function is defined everywhere there in the interval, the limit exists, and the limit and the function value are the same, and then that the function is differentiable on the open interval. So if those two conditions are met, then what's guaranteed is that there's at least one x value in the open interval AB, so somewhere in the interior of that interval, such that f prime of c will be equal to, you can see there, f of b minus f of a over b minus a, okay? So you can see that we're talking about graphically, all right? We have that the secant line, the line connecting the endpoints on the function on the interval, and the tangent line at c will have the same slope, all right? So a couple interpretations we kind of want to think about what this is, but you got to think mean, right? Mean is what? That's your average, right? So what is f prime of c, right? F prime of c is your instantaneous rate of change of f, right? At x equals c. And then what is this? What is f of b minus f of a over b minus a? This is your average rate of change of f from x equals a to x equals b. So we have here that the mean value theorem, what it guarantees is that at some point in between a and b, the instantaneous rate of change will equal the average rate of change of the function over that interval, okay? This is another one of those kind of we call existential theorems that guarantees something exists, but not necessarily how to find it. And, you know, a kind of trivial example of this would be that if you go through a toll booth here, right, at point A, and that's when t equals 0, and then you travel over here, some rate, right, at t equal at point B, and let's say this is at t equals 2 hours, okay, and let's say over the course of this that the distance here is say 160 miles, okay. Well, based off of that, then we know that the average velocity or speed, right, that our average velocity, our average rate of change of how fast we went would be 80 miles per hour. Okay. Okay, well, that makes sense. Now, by the mean value theorem, well, the function, our process of driving from point A to point B, right, is a continuous one, right? In order to get from point A to point B, I have to go through every point in between. I can't jump over any of these points. Okay. And also, it's differentiable because differentiable would mean that at any given point, right, as I'm driving along here, at any point in time, if I look at my speedometer, there's going to be some rate of change, right? So that would mean there's some instantaneous rate of change. There's some slope, right? But there's some rate of change. That means we're differentiable. So by the mean value theorem, what this says that, well, if I average 80 miles per hour going from point A to point B, then there has to be at some point in here, right, at some time, right, some location here that I was going exactly 80 miles per hour. Not 80 factorial, 80 miles per hour, right? But that had to be at least one time I was doing that, okay? So you could think about the context of going down the parkway maybe, and you go through, you know, easy pass over here, right? And it's time stamped, and you go through easy pass over here, okay? Well, if your average rate of change was 80 miles per hour, then that means, well, on some road where maybe the speed limit's 65 miles per hour or 70 or 75 miles per hour, you were guaranteed to have sped and gone over the speed limit, okay? So you get a ticket in the mail, all right? That is kind of the idea here. We could look graphically, right? Graphically, we have this over here. That here's my function, right? I have a couple different lines here. Let's move that out of the way. grab that one. Let's move that one out of the way. So here's my curve, my function here from point A to point B. So if I connect those 2 points there, right, that the slope of that line right here, the slope of this line, right, that's going to be your f of b minus f of a over b minus a. That's your secant line, we call it, right? But the slope of that line represents the average rate change of this function on the interval a to b. And this is a continuous function, right? You could see it clearly. It's nice and smooth, so it's differentiable. So that means at some point in between a and b, in this case, maybe right around here, if I go up to the curve here and I draw a tangent line, that this line, right, and the slope of this line is going to be f prime of c, right, that these two lines are parallel, okay? So graphically have that interpretation, okay? But again, the instantaneous rate change is going to equal average rate change. So anytime we're dealing with, something where you have to show that the slope or a certain value exists in terms of a rate of change and why it has to exist on some interval, we got to be thinking mean value theorem here. A couple examples of applying this to functions and whether you have to find the value c that's guaranteed, right? This is the value that's guaranteed to exist somewhere in between here, whether it's just finding this x coordinate or maybe finding the equation of the tangent line. I'm going to walk through 2 or 3 of these. Work's already done, but we'll talk about it and look at some graphs quickly. Okay, so over here, this first one, got to move the screen up, I guess. Away. Right there, okay. So here we have for this function below, right, on the indicated interval, we want to find all values c that satisfy the mean value theorem, okay, and the mean value theorem doesn't apply state y. So in this case, how do we know the mean value theorem applies? Well, if we look at this function here, right, this is continuous, right, because it's a polynomial, right? Think about if I evaluated this function for any value between -1 to 1, including -1 and 1, all right, the function would be defined, the limit would exist, and they would be the same, right? You'd find the limit of this for direct substitution, so it'd be continuous. Now, you're not going to know if necessarily a function's differentiable until you look at the derivative here and say, all right, is this function differentiable between -1 and 1? So on this interval, right, is this function defined, right? And it is. So in this case, function f is continuous and differentiable. So then by the mean value theorem, okay, so in terms of like justifications, since f is continuous on -1, 1 and differentiable on -1, 1, the mean value theorem applies, right? So we got to make sure we know why we can do this stuff. So now what's the mean value theorem is then guarantee that there exists some c, an x value between -1 and 1, such that the instantaneous rate change, which is your derivative, equals your average rate change, which I have over here. Here's f of b minus f of a over b minus a. This is nothing more than y2 minus y1 over x2 minus x1, right? Slope between 2 points. And we come up with this average rate of changes in here, -1. That's your average rate of change, right? So the average rate of change of that function from -1 to 1 is in fact -1. And then what's guaranteed is that there's some x value here, right, where f prime is equal to, and this is your f of b minus f of a over b minus a. So your instantaneous rate of change f prime is guaranteed to be equal to what? -1, your average rate of change for some x value between -1 and 1, okay? And we only want to concern ourselves with the values that are between -1 and 1. If there's values that make this true outside of -1 and 1, that's great, but it's not what's guaranteed. So we do the algebra, we solve here, we get x equals 1 and x equals -1/3, okay? And 1 is not between -1 and 1. So in this case, the value that's guaranteed by the mean value theorem would be -1/3, okay? So in this case, just recapping, our instantaneous rate changed, our derivative is equal to our average rate change, right? That's guaranteed to be true for some x value between -1 and 1, since function f is continuous on -1, 1, the closed interval, and differentiable in the open interval, okay? Now, just to look at this graphically, if we go over here, Here's our function on the interval -1 to 1. So if we graph that function, that's what it would look like. All right. Now, if I connect the endpoints, we can look at our secant line. All right. There's the secant line, which has a slope of -1. All right. So the slope is -1. That's the average rate of change of the function. All right. Right there. And then, all right, if I look at a tangent line, okay, and start at the endpoint, what's guaranteed is that as I move along this curve, right, as I move along this curve, this tangent line, at some point, that tangent line is guaranteed to be parallel. Looks like right around there somewhere, right, somewhere in that area, all right, at least one time. Now, in this case, if I go on now, and as I get this way, you can see that the other place I get is at the endpoint, right? But that one's not in between. So we go back here, we can see, just looking at this graphically, it looks like it's somewhere right around here. So if we use this just to approximate, it looks like somewhere around there. And clearly you can see that what? It's right there what we thought, and got analytically -1/3. So if I go back here, I replace this with -1/3, all right? And we can see there that these two lines would be parallel. So there's a graphical interpretation, right? That the secant line, the slope of that is the average rate change, and this is the instantaneous rate change, okay? All right, let's jump back over here. All right, here's another one. We got a radical function, right? Now in this case, we're looking from 3 to 11. This function is continuous from 3 to 11, right? This function would be defined. If I thought about how I would find the limit, I would direct substitute, I would get a value. So that's going to be continuous. If I find the derivative, right, here's f of x, here's f prime. I look here, right down here's f prime. I say, all right, what about this? Where is this defined? Okay, well, I know that the radicand part is defined for x greater than 3. Okay, that if x is greater than 3, then this function is defined. But at 3, when x equals 3, this function's undefined, f prime. Okay, except it doesn't matter because I'm looking for it to be differentiable in here. So for any of those values between 3 and 11, this will be defined. Okay, so it's continuous, it's differentiable. So the mean value theorem applies, which says that at some point, at some x value between 3 and 11, so in this interval, the instantaneous rate change, which is your derivative, is guaranteed to be equal to your average rate change, which I have up here, f of 11 minus f of 3 over 11 minus 3. The average rate change is 1/2. That's your average rate of change. So then if we set the instantaneous rate change right here, our derivative, equal to our average rate change right here, and I solve that, I come up with x equals 5. And you can see that 5 is between 3 and 11. Okay, so this would be the value that's guaranteed by the mean value theorem. All right. And I'm going to move to the next one. So if you need to pause, rewind, by all means, go ahead. And then the last one over here. Okay, now in this one, we'll find the equation of the tangent line to the function f of x on the closed interval 0 pi at the point that is the solution to the mean value theorem. Okay. So in this case, we have this function f, which is continuous, right? 2x is a continuous function. Sine of x is a continuous function. So collectively, all that's continuous. When I find the derivative right here, I say, all right, what about this on the interval 0 to pi? So on that interval, is 2 plus cosine of x going to be defined? Yep, cosine's always defined. Plus 2 is always defined. So it's differentiable. So mean value theorem applies. So I need to find the average rate of change. Right here is your average rate of change. We go across here. So our average rate of change is 2. So on average, over that interval 0 to pi, we go up 2 units. For every 1 unit, we go in the positive direction. So I set over here my instantaneous rate of change, 2 plus cosine of x, my derivative, equal to my average rate of change 2. I solve for that. I get cosine of x equals 0. And the only solutions for cosine of x equals 0 in the interval 0 to pi, think of your unit circle. If I start here and go over here, what point do I have an x coordinate? Because cosine is my x of 0. Well, that's going to be right here at your pi over 2, right? There's pi over 2. So pi over 2 is the x coordinates guaranteed. So now I want to find the tangent line at x equals pi over 2. In order to find a tangent line, I need a point and a slope. I already know the slope because I just solved this. The slope is going to be 2. So I have the slope. So the only thing I really need is the point. Make sure that you plug it in the correct place. Right? I don't want to evaluate f prime of pi over 2. If you evaluate f prime of pi over 2, you're going to get 2. That's what we just solved. All right, so I'm going to do, it's a quick tangent line on the graph of f. So I got to plug pi over 2 into function f. So I do that. I get pi plus 2. And here we can see that in point slope form, that would be my solution. There's no reason even to put this in slope intercept. Okay, that is going to be the equation of the tangent line. So in other words, this tangent line, when I graph this function, the line would be parallel to the line that connects the endpoints on the interval 0 to pi. All right, so that's essentially initially what we have to do here, right? Applying the mean value theorem, how you know it applies. Make sure this is going to be something that in on the AP test that you have to cite, right? Why do you know you can use the mean value theorem, and why does the mean value theorem apply? That the function is continuous and differentiable on the closed and open interval respectively. Another way you could see that stated, okay, is that if you're just told, like for instance, this one, there might be times where you don't have, let's say, analytically the function, but maybe it's from a graph, or you just might be told that f is differentiable on some interval, right? So you might be told this, like f is differentiable on AB, or f is differentiable on the real numbers, right? And then what you would state is, since f is differentiable, it is therefore continuous, right, on the interval, okay? And then that's how you get your continuity justification, right? So that if you're just told the function is differentiable, that you have to state that the differentiability implies the continuous, and you could say, f is differentiable implies f is continuous, therefore by the mean value theorem, ... right? And then you could go do your work, right? But you got to show that kind of justification and why you know it applies, okay? So watch this, check this out. Initially, it's pretty straightforward here. This is going to pop up. We'll practice some more in different contexts. Table of values, this kind of thing, where you're asked to show why maybe the derivative has to exist on an interval to be a certain value. And it's because, well, if you have a table of values, you can find the slope between endpoints of values, right? And one last thing here I want to mention is, if a function's continuous on 0 to pi, then it would be continuous on any subinterval of 0 to pi, right? And likewise, if it's differentiable between 0 and pi, then it would be differentiable on any subinterval of that. So it might not be just that 0 and pi it works. If we had a table of values, every other interval, subinterval, the function would also be continuous and differentiable. So the mean value theorem would apply on those subintervals as well, those smaller intervals. All right, and we'll look at some of those. Like I said, watch this, check it out, and we'll practice some problems, a couple here, and we'll be moving forward, okay?